energy in simple harmonic oscillator. Okay, write down the topic in your notebook. Energy in simple harmonic oscillator. So, if I'm saying energy, in our previous chapters, we considered both kinetic energy and potential energy. Am I right? If I want to get my equation for energy, I have to add both the equations for kinetic energy and potential energy. Is it clear? So, the kinetic energy and potential energy values, they are varying from 0 to maximum. Are you all agreeing? This kinetic energy values and potential energy value of a particle varies from, it will vary from 0 to a maximum position or 0 to a extreme position. Okay. So, what about velocity? These values are varying from 0 to maximum. What about velocity of a particle that is executing SHM? It's at the main position, its velocity will be 0. Very good. And at its main position, its velocity will be maximum. See, while the object, while it is at its mean position, its velocity will be maximum. And when it is at extreme position, its velocity will be 0. Okay? Consider, keep these 2 points in your mind. Now we are going to arrange the equation for expression for potential energy separately, expression for kinetic energy separately. After deriving both the expressions, we are going to add those expressions for getting total energy so that we can arrange energy in simple harmonic oscillator. Okay. While we are calculating expressions for potential energy, separately I am going to calculate potential energy in terms of displacement and potential energy in terms of time. Am I right? Since it varies between displacement and time, how we are drawing the graph? How we are drawing the graph? Time in y-axis and displacement in x-axis. Go through our previous graphs. So, while I am deriving expression for potential energy, I am going to derive in terms of x and in terms of t. Okay? Like the same for kinetic energy also. Then we are going to arrive E of x and E of t finally. Okay? Let me see how we are going to derive this. Expression for potential energy. How can we denote potential energy? What's the symbol? Very good. U. Expression for potential energy. U. So, for arriving this expression, first I am going to write Hooke's law. Hooke's law or potential energy in a spring. Go through your 5th chapter and find out the expression for Hooke's law or potential energy that is acting in a spring. In your book, it's given in page number 80. Okay, part 1. Hooke's law or potential energy in a spring. Yes, ma'am? Is it correct? F of x equal to minus k of x. But here, s will be given. Am I right? S was there in your notebook. Check your notebook. Whether it 4th chapter, 5th chapter, work done is there in your notebook. You can check for this law. Potential energy in a spring. F of x equal to minus k of x. Okay? This is the familiar Hooke's law expression. This I am going to take as equation number 1. Okay? Next, I am going to consider work done as a conservative force in terms of potential energy. equation is du by dx equal to minus ax. F of x equal to minus du by dx. You can check in your notebook for this equation also. This is worked as a conservative force. Conservative force means what about the relationship between field and the path? Will they be dependent or independent? The field will be independent of the path. Am I right? This is a conservative force. So that time the equation is f of x equal to minus du by dx. Both the equations we discussed in our fifth chapter. Okay. So this one I am going to consider as equation number 2. Can we compare both these equations 1 and 2 since the LHS is same? Yes. So next one, comparing 1 and 2. How I can write? Minus du by dx equal to minus ax. Can I write like this? Since LHS is the same. Can I cancel the minus sign? So du by dx equal to ax. This I calculate. If I differentiate this u in terms of x, I am going to differentiate this u in terms of x. So u of x equal to ax into dx. My du will be kx into dx. So if I want to differentiate this, u of x will be kx into dx. Okay? Within the limit 0 to x. Where k is the spring constant. Yes, you all know. Am I right? Where k is the spring constant, and the spring constant let us to know about the stiffness of the spring. Am I right? That we have discussed in force law for SHM. Spring constant na k that describes about stiffness of the spring. Yes. Now by u of x will be, and since k is constant, I am taking it outside. If I differentiate x, it will turn into x squared by 2 within the limit 0 to x. So u of x equal to 1 by 2 into ax squared. That is be my third equation. If I differentiate in terms of 0, it will be 0 square. So since it's meaningless, I am avoiding that. I am writing x square term alone. Upper limit alone I am writing. Okay. So in our previous case force law for SHM, I wrote the equation as x of t is equal to a cos omega t. Am I right? Turn your pages and look. That's velocity, ma. For displacement x of t equal to a sin omega t. Okay. Whether I wrote it as a sin omega t or a cos omega t? A cos omega t. Since both sin and cos are periodic, I can take any one equation. So for this expression, I am going to take x equal to a sin omega t. Okay.
present there in equation 3. I am substituting this equation here in equation 3. Okay. So the
term consists of time, am I right? So instead of x, I am going to write it as u of t. Now I am going to find u of t, potential energy in terms of time. Already we found out potential energy in terms of displacement. Okay. If I substitute this equation, I can arrive my potential energy in terms of time. So half k. Can anyone say if I substitute this equation here, x square. See, this is the equation for x alone. This is x square. A square sin square omega t. This is my equation number 5. These two are important equations which we are going to substitute in arriving energy for SHM. Okay. Now I am going to draw a graph for u of t. Okay. Since sign is involved here, how the graph will look like? Any idea? Very good. So t is in x-axis and energy in y-axis. Since it's a sine wave, it will start from 0. Okay. My graph will look like this. Okay. This is the graph for u of t. So can anyone say why the only positive cycles and no negative cycles? Energy cannot be negative. Very good. So from this equation, if you see, sine square is there. Am I right? If sine is there, one positive, one negative will occur. Since sine square is there, negative cycles only occur, only positive cycles on the x-axis. Okay, that's the one more reason. Energy cannot be negative. From that itself we can draw. But since sine square is there, only positive cycles will go negative.